Well, good morning. Thank you for showing up on this exceedingly warm day outside. So my outline is to start with a little motivation of why we would be looking at this approach. Then we'll go to the food material science approach and why that's important. Move on to give you some examples, and then we'll look at some of the research gaps and what we could be doing in the future to fill those gaps. Okay. I like the idea of planet Earth as a closed system, as an ecology concept, that we have anything we do affects everything else. So if you look at our surface area, you know, about a third of it is land, and of that, what we use for agriculture, 2/3 of it we use for grazing. It's only good for grazing. The other third is for our crops. So when you start looking at the amount of land we really have available for crops, it's actually very, very low. The other thing I think is interesting is if you look at our current population, about 7.7 billion, I asked myself, well, when was it half? And it was half the year after I graduated from high school. So in my adult lifetime, I've seen the population of the world double. And we're going to 9.8 billion estimated by 2050, and that number keeps on going up. Each time you want to look up something like this, it keeps on going up. Okay? So we have to ask the scientific question, what is the best food system to feed the current and future world population? How do we address this? So I kind of build on the general concept of food system as three critical elements. We've got production agriculture, food processing in the middle, and then human consumption on the other extreme. So with that in mind, an ideal food system evolution, how we would develop that system, is we start with the input, the end outcome of what we want to have. So research in nutrition and health provides information on the amounts of nutrients, types of food structures, matrix, because that's important too, needed to feed this number of people. So we need to know what we need to produce. That should feed back into classical agriculture and new approaches to produce those amount of nutrients and food structures. And then, as the food scientists in the middle here, two elements here. One is stabilize the desired biological structures. With that, I mean, if we look at our productions of fruits and vegetables, fresh fruits and vegetables, how can we stabilize those structures so they're desirable, so that they maintain their nutrient content, and then convert these foods that are into other types of foods that's from a raw material that are safe, available, affordable, healthy, desirable. Okay. But there could be a joke that a production agriculture scientist, a food scientist, and a nutritionist walk into a bar. And the joke is that we never get together and walk into a bar. We tend to be three separate worlds that seldom talk to each other. And I think that's one of the themes that I want to put together today, is that all three of these groups have very good desirers in addressing the world food needs, but we seldom talk and coordinate. And if you look at the food system, all of those desires need to be coordinated. Okay. So let's look at some current trends and desires. And put this together with the help of my wife who's here, and she does a really good job in finding images. And I said, well, let's convey something in this first image. So there's our nice animals that we tend to like, okay? Because we think of animals as pets now, right? We seldom tend to think of animals as food because most of us are pretty much disconnected from that. So if you take that animal and convert it directly to food, you don't feel as comfortable looking at that. But then if you put it into something like this, it loses the animal identity, okay? Here's the other extreme. Here's an animal that we don't mind killing as much as we feel uncomfortable killing that one. So we're probably, all of us in here have squashed a grasshopper at some point in time in their life. But when it's cooked, it is really, and it still looks like something we don't want to eat, but then we got this concept of powder. Anything turned into a powder turns out to be a good way of dealing with a uncomfortable biological material to eat. Okay. So one of the big pushes now is, okay, we don't want to deal with the animal, let's grow the tissues directly in some type of cell culture. So that's a big push that's going on, and no telling where that's going to go, but it's still a long way from having the scaffolding where you have connective tissue and your cells, just like what we have in plants, what we have in muscle tissue, that steak-like consistency. But we also have this exploring other areas of plants that we have not maybe eaten as much in recent times, and then going to other completely different sources like microalgae. Okay. We want to put all of these things, these powders, these materials into food products, and there's some out there on the market. So there are chirps made from crickets. We have ancient grains, and this is another ancient grain product. And this is just the idea that we can put some of these things into beverages. Okay, I see some cringes in the audience there. Okay, okay. Okay, so how are we going to do this? Well, let's start about what we're trying to do. So if we have foods are going to have properties. Okay, and one of them is quality. We have this idea of preference, what kind of foods we like, but when we make them, we want to stabilize them. That's my granddaughter when she was about a year old, and she was enjoying her yogurt all over the place, mixed with Cheerios. Okay. She still has the same attitude, and maybe it's gotten worse as she's gotten older. Okay. Affordability is one of the key elements that we always have to consider. Our health benefits, what this group knows about quite extensively, but also now we have this societal driver, concept of sustainability, a group of people that want to be vegan, a group of people want to keep kosher, a group of people that want to avoid GMO type of products. So all of these properties need to be balanced when we put together our food supply. Okay, so where am I coming from? I'm coming from more the physical chemistry side of this, and look at food from a structural basis. So we look at food structures across length scales from molecular to macroscopic. So here we see very macroscopic. Here we get down to the more on a few hundred micrometer type of scale. And that's all different levels of structure that we can define. Why is that important? Because built into those structures are the properties that we like, the properties that we need. So built into that structure is temporal delivery of our main sensory sensations, delivery of our nutritional compounds, our bioactive compounds, but also built into that structure is what we expect the food to do. For example, if we've got a cheese, maybe a certain type of melting. So all of these elements have to be built into that structure if we want it to perform. Okay? So how do we get there? Well, we have manufacturing processes that take molecules and put them into these structures, but also remembering that we have a biological process that initially generates the materials. So this gets back to this whole idea of where we wanted to go from production agriculture to food science to nutrition. So it's looking at the biological processes that produce the molecules, how the molecules are then produced to the food structure, and then how those food structures generate the properties. So a food material science approach is we have agricultural materials. This kind of say it's a whole palette there to pick from, okay? Are processed and properly mixed with other ingredients to produce structures that have desirable properties, okay? And it's material science because this general idea that we can take a range of materials to produce the end product. So we can summarize this by molecules, by either biological process like growing a plant or manufacturing process like making cheese, produce structures. These have certain inherent physical chemical properties that when consumed through oral processing, we get structural transformations. And then this goes into consumer preference and also digestion, absorption, delivery of nutrients. So we have two paths here. We have the molecules to structures, and then the structures to biological function. One of the big challenges we have is that a lot of times, especially in food science, we just stay along that path right there, and we don't evaluate going down that other path. Okay. So what are our operating hypotheses? Are that properties are associated with specific structures, processes produce those structures, and often a range of molecules can produce those structures. So that gives them the flexibility of making a dairy-like product from a plant-based material, for example. Okay. So it's molecules, processing, structures, properties. Okay. Material science. Why do we have this concept? Well, material science, it basically fits what I was talking about on different length scales. So let's look at something like concrete, okay? So we could take concrete and we can make a road. We know it makes a pretty good material for a road. However, we also know that we could build it into these blocks, and these are going to be our intermediate structures, and then we can take those blocks and build houses and other things like that. Okay? We can modify the concrete such that we can get this beautiful countertop, and they have different types of textures in that there, so we get two elements built into it, not the homogeneous element up at the top. Or if you're really creative, you can build a canoe out of it, knowing the ideas of buoyancy and how something like that works. So it's flexibility on what we produce from the same base material. Okay. One of the key things is this meso-middle structure. So you could, in theory, build this wall by pouring it directly, but by using these blocks, we have the ability to have a much more flexibility in the structures we build. Okay. So if we now do that and put that into foods, we hit into an area that's called soft matter physics or soft condensed matter physics, which is really important about the length and time scale of the elements. And any time you go into physics, you're dealing a lot with lengths and time scale. So what we have right here is just the length scale. So we have molecular down here. We go to the mesoscale in here, particles from an emulsion, a gel network, aggregates, foam, and an aerosol. And here's our macroscopic, what we can see on the length scale with our vision. Okay. So if you look at some basic taste and aroma and basic touch, like viscosity, we can relate those to molecular characteristics. Okay? So we can look at a structure of a compound that's supposed to be sweet and tell you why it's sweet, or if it will or will not be sweet. Okay? Taste and aroma release, and touch and texture and sound come in the mesoscale structures. You actually need cells to get sound. So anything that's crunchy that you eat, for a carrot or a potato chip, has cells that are rupturing, and you get that sound coming from it. Okay? And then at the macroscopic scale, you've got appearance, stability, and again, notice that texture goes across all length scales. Okay? Macroscopic properties are predicted, modeled from molecular properties, are not predicted or modeled from molecular properties at the mesoscale structures. That's the key soft matter physics approach, that we have to understand what's going on here to get this. What's good about that is that it says if we generate a structure, again, from either ground up crickets or a nice plant source that gives us the same structure, it should be able, in theory, to produce the same outcome. Okay. General approach, identify properties, determine structures responsible, determine how to process it, determine molecular properties needed to form the structure. So kind of going in this entire circle. Okay. So I like to segregate foods into more of a physics concern, and this is tying in with how we eat them too. We have liquids, semi-solids, soft solids, and hard solids. Okay. Liquids are pretty easy between biology and just what we can make. Okay. Hard solids are pretty easy too, but the intriguing thing is when we get to hard solids, you know, what happens if you take away moisture from the carrot? Does it get crunchier? No, okay? If you lose your turgor pressure, you get a limp carrot that doesn't crunch. But you need to take away moisture to get these to crunch, okay? So we have this desire to like hard solids that crunch, and there's a lot of psychology with it. But the great thing about fruits and vegetables is we get it at a very high amount of water. The bad thing about it with everything else is we get it with a very low amount of water. So essentially you could take about 100 grams of cookies and compared to 100 grams of carrots, and the weight and the caloric difference is just amazing. Okay. Soft solids, these aren't crunching, okay? Very complex structure. This was the hardest one. In fact, I think I'm semi-cheating on this. But think of all the semi-solids. So yogurt, what else do you eat? It's not a hard solid, it's not a liquid. What can you name something?
Mayo.
Excuse me?
Mayo.
Yeah. Puddings. Okay. Ketchup. We have a lot of soft solids, okay? Excuse me, a lot of semi-solids here. Biologically, it's kind of hard. They tend to either be a soft solid or liquid. So, you know, kind of an overripe banana maybe gets it. So it's interesting that a lot of the textures that we eat, and these are very easy to eat very, very rapidly. So all of your desserts and all of those things like that. Okay. But the other thing we always have to remember is that structure doesn't stop at what we can see, but it goes down to different levels of length scale. Okay. First example, beverages. Okay. So molecules of structures is what I'll be discussing. Okay. So if we start with the bottle of water, and one of the things that I always liked to do when I was teaching food chemistry was talk about why Dasani water and Coca-Cola out of the machine had the same price. And the students were down there writing. I said it's because they have to take that Coca-Cola, extract out all the sugar, the colors, all the flavors, so they get down to that Dasani water. And the students, of course, would be writing it all down. And then one of them would kind of go, wait a minute. So anyway, so there's our basis right there. We've got water. We have soluble molecules that go in there, okay? We have polymers that can go in there, and then we have different phases, okay? We can have an emulsion in there, like in whole milk, where we've got fat. We could have solids in there, like chocolate milk, where we've got cocoa particles. We can have gas in there, where we have our milkshake, where we've got some air phase in there, okay? So those are the components, and they're on different length scales. These are very, very small. These are getting to be bigger. Here we're at a colloidal size. Okay. So as an example, Nesquik, there's the ingredients, and so you can kind of break it down. We see we've got actually, and this is kind of intriguing, you've got a whole bunch of color right there, sugar, usually some salt, lowering the pH, some flavor. Anybody know why that's in there? Yeah. Yeah, it's a preservative so that when you're having it out, it's inhibiting growth. Okay, if we go, the polymer is xanthan gum. Okay, we'll talk about why that's in there. And our dispersed phase are cocoa solids. So you can take any beverage and pretty much break it down to some elements. So what do we want in a beverage? We want it to be either clear or opaque. We want it to have a shelf life for so many months at a certain storage temperature. We got our viscosity mouthfeel. This was all based on protein beverages, so percent protein, other ingredients. And each time you add complexity, you get into more of a challenge on stability and everything else. Okay? And so for example, particle size, and actually the contrast and refractive index is going to be determining the appearance. And this is just showing with proteins that as you increase particle size, in this case by lowering the pH, you get a large amount of turbidity. You're not adding a pigment, you're just adding more light scattering to the system. Okay. Now, what could go wrong? So there's one from an experiment we did where we had an interesting little treatment. 6 years old, that one was still in good shape. Didn't fall apart, okay? The control within a short period of time turned into a gel, and notice the importance of light scattering. That's the same amount of pigment in both of those, but because of the light scattering, you got the difference in appearance. Another problem you can have is aggregation and precipitation coming down. Or you can have protein polysaccharide sagregative phase separation, where the protein and polysaccharide are separate polymers that are not compatible. They each grab a chunk of the water and separate into different phases. Okay? You basically don't want any of these to happen unless you want to say something on a label that after a certain period of date it becomes something to chew on. Okay? When we start looking at conditions that allow for this, we've set up this phase diagram type of approach. And what this shows is the relationship between protein concentration and pH at a given thermal process for a certain type of protein. And this was a very simple type of system. So if we start right here, we see, well, there's only these zones right here where it's homogeneous. In other words, it's still a fluid. It's turned into a gel there, it's turned into a precipitate there right after we heated it. Okay? This tells you the appearance, and it says, well, we're going to have to go to very low pH if we want it to be relatively clear on low turbidity. This is a solubility indication, and it says that, you know, if this is our highest solubility, if we want it to be stable, we need to be more in that region and in this region right there. So you start seeing your limitations of what you can put together. Now, if you throw a bioactive in there, a polyphenol, it may expand the range of this, or it may shorten the range. It may cause more aggregation, or it may limit the aggregation. Okay. So what's going on from a protein standpoint? We got native protein that's going to be natured, it's aggregated, and then what we really want is the soluble aggregates, not the large ones, not the gel network. Okay. So the defining physics of this is Stokes Law, which very simply says that any particle that is in suspension is driven by several forces. And the first one is the density difference between the fluid and the particle. This is really hard to regulate. You can do it somewhat. You can make fluffier particles, but not very easy. Does anybody know where this comes in emulsions in food systems? So what do they do in food emulsions, especially if you drink Mountain Dew or something like that, to decrease the density difference between the surrounding fluid and what's called a citrus oil? Have you ever heard of brominated vegetable oil? It's one of the things that the food babe just had a pitch to fit about, that we shouldn't be having this in there. Okay? So what they do is they brominate it. It's got a bigger nuclei, so its density goes up. So you can get, so the other thing this tells you, if you've got isodensity, so if you're the same density, nothing goes anywhere, right? If you're up in space, the force of gravity, you know, so emulsions are more stable in space than they are at home. Now, getting up there probably destroyed all the emulsions anyway, but if you can make your emulsion once you're up in Skylab or Space Lab, it'll work pretty well. Okay. The next one is the radius and the radius squared. This is a key factor. This is why we want small particles. This is just showing you, I did a calculation for a theoretical amount of precipitation, that if you've got some particle at 100 nanometers, you got 2,000 days, go down a log with 320 nanometers, down to 40 days when you go up to 680 nanometers. We're still below a micrometer in particle size. So that's very important because it's a squared function. And the one that a lot of times that different beverages work on is this viscosity of the continuous phase. This is a Newtonian assumption, but so if you put in non-Newtonian fluids, they're very viscous at low shear, so that could put in a yield stress or a weak network. And basically, if you have a net around this system is what that would be conceptualized as, it's not going to go anywhere. So that's why that xanthan gum was in that Nesquik. Okay. So if we want to minimize this, okay, so we try and make these as small as possible, and then once they're made, we try and prevent them from secondary aggregation with electrostatic or steric stabilization. Both of these forms of stabilization, when two particles get close together, there's forces that push them apart. So that's kind of the goal, minimize secondary aggregation. Okay. So one of the approaches is to form these small, highly charged particles, and this gets into protein polysaccharide, and we use pectin as our polysaccharide and whey protein. And you have this is a Goldilocks type of effect, where too much and too little, you got to have it just right. Okay? So you want them to be these soluble complexes right here, and this is this pH. If you go too low in pH, you get an insoluble complex being formed. You could go down lower and it would be soluble, but probably you're not getting a whole lot of benefit from even putting it in there at that point in time. If you go up higher, it's also co-soluble, but then you get to this problem of the segregative phase separation. So for a protein polysaccharide system, there's going to be a little window of pH, and there's going to be a window of concentrations where everything's fine and comes together. And just as an example of this, this is some work that we did where we took a whey protein and a high methoxyl pectin particles, pectin, and put them together. We complexed them, heat set the complex, adjusted to the desired pH, and then in 6 seconds at 141 degrees C is a pretty tough, actually, heat treatment. And as you can see here, the unheated and the pH 4 were exact same particle size. So that worked. That worked really well. That's one example. Okay? So it was a combination of the electrostatic, the charge, and the steric, the polymers pointing out in solution, preventing each other from interacting. Okay. Now, let's go to all these plant-based material beverages. Okay. If you're in the dairy industry right now, there's a lot of push against calling these things milk. People don't like that because it's definitely not. You don't tend to milk a oat to get at least the best I can tell. You can't get much milk out of oats. But anyway, I think that problem that the cow has already left the barn in that one, shall we say, because people already view it like that as milks. But the idea is a milk type thing is that opacity is expected, which is good because it allows for the particle size. But then we get to our universal challenges with stability. And I imagine this is just some that I got this nice image from, and I'm sure there's many more on the market too. So if we look at this, here's something, hazelnut, plant-based beverage, water, rice sweetener, rice bran, ground roasted hazelnuts, and then we've got gellan gum, locust bean gum, and sunflower lecithin and xanthan gum. So we have several polysaccharides and a surfactant in there. Okay. So now, if we go to this, so the grinding and possibly lecithin and processing determines the primary particle size. Aggregation may or may not occur during storage. The polysaccharides, which would be the bran and these different gums, are determining the flow properties of the continuous phase. So I can pretty much look at the ingredient labels and tell you what each component's doing in the system on that. But, here's the interesting possibility. What if we could do this? Okay. What if instead of doing all of that, so what do we have to do? Well, we're afraid of this thing falling down too fast, so we really want to regulate this factor right here. And we do that by adding in gelling gum, locust bean gum, and xanthan gum. What are they? They're polysaccharides. Okay? What if we could generate hazelnut fiber? Instead of having to go outside, we start our base material, and this is the other concept I want to get together today, is that this minimal processing, or keeping it within the plant system. What if we could take that plant, or take that plant material, and say, how do we best get fiber from it?
You don't need the internet by any chance, do you?
No, I don't.
Good, because it's down.
Okay.
I'm sorry about that.
No problem. So this would be a very interesting challenge. Can we either get the fiber from here? Can we somehow get it from the shell, some kind of recovery process? Could we get it down that we have these very minimal type of labels? I think that's one big area for future research. But like most things, it's easier to define the problem than to develop the solutions, because I think there's a fair amount of work that would need to go into that. But in theory, there's no reason why we couldn't do something like that. Okay. So now let's go, that was an example of going from there to just the initial structures. Let's go all the way through, and with one of my favorite things, cheese. Okay. Okay. Low-fat cheddar cheese that funded a lot more researchers than it did success in the market. Okay. And this is from market samples, and the question we were asking, because we have different bars here, was if you fed them like a cube versus a thin slice, could you tell a difference on liking? And obviously you can't. So this is the full-fat cheddar cheese, there's the liking, there's the reduced fat, and then there's the low fat. So it just goes right down. Same thing for flavor, same thing for texture. This is overall. If we did texture, it looks exactly the same. If we did flavor, it looks exactly the same. Okay. Didn't work. Don't like it. Okay, so what's going on? Well, this is looking at textural properties. And I want you to, so we've got these properties here: smoothness, how much it sticks to your mouth, the cohesiveness, how much it sticks together during chewing, and breakdown. We'll go over here. This is like the number of particles. This is how much force you have to bite. And then these two are related to kind of an elasticity or springiness. Okay. So watch what happens. So we take our regular cheese. We start reducing the fat. We decrease these and increase this. We go from more of a creamy, nice breakdown to more of a rubbery type of consideration. And we reduce the fat any further, so we just shift it over in that way. Okay, so can we explain these structural effects? So the first thing is just to basically model the structure. And we have models out there for this. This is a basic fill gel model. And we say we've got fat particles here, interdispersed in a continuous gel phase, and we have a volume of each of those in there. And if we look at the various models that are out there, we can find a model that says, yes, we can model how firm this is based on the storage, the firmness of the cheese versus the firmness of the gel phase, how much of the fat gel phase is there, and this crowding factor. Okay? So we can model, if we just like go on this back of this and just push. That's what's really easy to model, because that gets into the physics of the material. That gets into the importance of like your table, right? So you don't want a table that you put your arm on and it goes down about 1 inch each time. You want a certain rigidity to the system. So there's all kinds of knowledge of the physics of that out there. Physics of rigidity, physics of resistance to a little push. But when we eat it, we don't do a little push. That's texture. That's the breakdown. So what determines that? Well, to do that, we need to go to primatologists who have been studying the feeding behavior in mammals for a long time. And this is the prevailing model of that. So move food in the front of the mouth, okay? Initially hits palatable, yes, we get going. Unpalatable, no, we spit it out. Okay? Stage 1 goes to the post-canine area. Now we start our chewing process. We continue our chewing cycle until we decide that we can swallow it. Then it goes through and we swallow it. And you're going to see that here. So initially, you're going to see this is a solid coming in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then a couple of motions to clear. Okay? 13 chews. Okay. Now a fluid's going to come in. Comes a fluid, you see a large volume, shoo, goes right down. Okay. So now think about the physics of that. So what's important in texture? It's what happens along those 13 chews that goes back to your brain, and you say either this is good or this is bad. Okay. So if we look at perception of texture, and this is one way to kind of model it with cheese, this is just a factor where you're looking at the normalization of particle size, okay, area of particles. So you have a big particle at first bite, you comminute it down, you get to some type of regranulation. So the irony of most solids is we break them apart and then we have to stick them back together in our mouth, okay? So you initially comminute, you granulate it into a mass, it finally gets to a cohesive mass, and then our signals in our throat says it's safe to swallow. This is a very critical step, and in fact, in infants going into toddlers, you have to teach them how to swallow. You're basically, the foods that you give them are determining how they end up eating in some elements later on in life. So it's very critical because they don't initially know that swallowing threshold. It's something that becomes learned with the initial set of foods. It's not an inherent program. Okay. So texture is derived from structural transition pattern occurring during this. So now it becomes, the complexity continues to increase. So let's compare just on timing. The full-fat cheese took 12.5 seconds. The low-fat cheddar was 18.2 seconds. So it was a longer processing. Okay? So then if we put that kind of together, oops, go back. What we see here is that if we just look at these kind of first little terms right here, this model can pretty much explain how we can adjust those. But this is where it gets to be a problem because this is a breakdown pattern. This has got time elements to it. It's a temporal and spatial type of problem. Okay? So that's where we go into oral processing and measuring jaw movement and muscle activity. This is actually chewing of a food. We've got recorded from somebody we wired up. You can see we wire them up with electrodes here for muscle activity, and then we glue a magnet right there onto their lower jaw, and so that when they chew, we can trace not only the temporalis and masseter, but the digastric muscle, which we're down here. There's the magnet going. So we can actually follow that whole pattern during chewing and get these types of activities and measurements. So we can ask the right question on what's going on. So what happens with the low fat versus full fat? Well, just the total muscle activity is a lot more. So right there, your brain is saying this is taking a lot more work for this to be consumed, okay? However, if you look at the jaw movement, if you look at the pattern basically didn't change. So it's the same jaw pattern, just required more chews. So your brain's going, well, cheddar cheese should have been done a long time ago. This is not cheddar cheese. There's something wrong with this one. I don't like this pattern. And if you do the wonderful but revealing, a little gross but revealing, chew and spit experiments, you can also see that that reagglomeration, it happens really fast in full-fat cheese and very slowly in low-fat cheese. So again, we can define the problem, but it's really hard to generate that solution. Okay. So we can kind of summarize it that the difference is that with our full fat, we went for this transformation really fast, and with the low fat, it took a long time to finally get to this transformation and form that cohesive bolus. Okay. So now we're on the last little bit, and people should know this. What year? First man on the moon. 1969. Exactly. So that was in 1969. Also in 1969, this book was published called 101 Problems in Food Science and Technology. So this is the way the world was viewed when we had less than half the population we have right now. Okay? 186 scientists, not, and I don't mean this in a derogatory, not administrators, 186 in the trenches scientists contributed to this book. Okay. Here's what you find on the first couple pages. Research efforts of the kind outlined in the volume will aid materially in providing necessary scientific for the Department of Health, Education, and Welfare and other institutions to tackle many complex public health problems related to food supply. Secretary of HEW, Surgeon General. If that isn't a good letter to support your proposal for problems for research goals, I don't know, that would be perfect if we got something like that right now. So you're going to think, well, this is all going to be a bunch of nutritional type of goals. But no, these are mostly food related, more of a, I'd say, agriculture, food science, food perception related, okay? And here's one. I just picked out a couple to show you that sometimes things don't change. It's kind of this back to the future. So, culture of desert plants for food. So what are we trying to do now? Well, now we're trying to make the plants that grow in our normal climates adjust to climate change, right? So same type of concept, but what they're doing here, what they're saying is, well, maybe we're going to expand our agricultural land by growing things in the desert and eating that. Kind of an interesting approach. Okay? A new generation of restructured foods provide low-cost recovery of proteins, carbohydrates, and lipids. So that's what we need to get. Deal with what's called a protein gap. Here are some solutions. Single-cell protein, 1969. What are we talking about in 2019? Single-cell protein. Why are we not eating it? Unfortunately, none of these high-protein foods resemble conventional protein foods in appearance or flavor. Why are we not eating it now? Unfortunately, not a lot of progress in 50 years. But the other thing I think that's important is that it talked about the need to understand the biology of taste. And here, I love this. Recent developments in neurophysiology techniques have made it possible to record these nerves. So that was just at the beginning for them to start understanding and making these connections. Okay? And the last one is dear to my heart because it's texture. It says, well, this is very important. It may be the most important single factor. Measurement, specification, control. It still poses many difficulties, and information is almost non-existent on the physiological and psychological elements of texture perception, what I was just talking about. Okay. So last little bit, we're going to talk about the basic senses. So anytime you eat food, you've got elements of all of this coming into consideration. So we're going to focus on taste because it's a good example of the gaps that we have when we look at texture. Okay? So there's our basic receptors. So what do we know about sweetness? Well, back in 1967, we came up with this AHB, acid base a certain distance apart. It said that any molecule that has that type of structural relationship would be sweet. So that was an initial structure function type of model that was out there. And we knew we have at the macroscopic scale the tongue, and then we have taste buds, and that we have some kind of receptors in there. In the intervening years, we gained a lot of knowledge to fill in the gaps. Okay? We know it's a type 2 receptor cell for sweet, umami, and bitter that comes in. It actually crosstalks with the other ones, but there's a cell biology came in there. And then we get down to the molecular scale, there's a receptor docked with an artificial sweetener. So we can get down to that receptor level, down to that structure. So now we go and look at this structure based on various models and determine binding and how that then sends a signal up of sweetness into the brain. Okay. Well, now what if we want to do that for this texture breakdown pattern? Okay. So with that, okay, initially, so what I'm going to do is I'm going to throw these up there so I could go over and talk about them, okay? So these are our initial texture perceptions up there, okay? Then we start going in here, and now we get another group of mucosa that's got pressure sensors that we can pick this up. Now when we start moving it, we get our skin coming involved. We've got lining of the mucosa, masticatory mucosa, and then all of these other elements coming in, periodontal ligament. So we get signals coming in from all over the place on our oral facial. Okay. Not only that, we have different thresholds in different areas in our mouth. Okay. So this is the touch threshold here, and this is in grams. And so what you see is that you've got your thresholds right there, and then it changes as we go different distances. This is the 2-point threshold. So this is the distance between, you take two things and you put a stimuli there and a stimuli there. They have a way of determining what distance between the two stimuli you can resolve, okay? And you see that this is very close in here and much wider back there. So it's not like we've got this one little sweetness receptor that binds a molecule. We've got all kinds of information coming in for texture on the physiological side that needs a lot of work to understand, okay? So the real trick that we have in the future from the biology side is understanding how the structure transition pathway translates through these receptors, through the cells in the oral cavity to give us this perception. Okay. The very last bit is talking about similar products made from different materials. So on the market right now, you know, you've got gluten-free bread, you've got vegetable protein-based burgers, you've got the beverages, you've got vegetable-based dairy-like products, okay? So the approach would be to start with defining the properties, okay? Go through this process and then determine if the target structures with desired properties can be created by other molecules. Essentially, putting together the path that I had discussed before. However, what do we know? There's just two things I want to leave you with. One is that if not many people ever associated much with the dairy industry in this group, but they had this idea of what's called recombining. Okay? So if you're in a place in the world where you don't have a lot of milk, you can get milk shipped to you in the powder form, so powdered milk. So then the question is, can I, instead of starting with the milk that has never been dried, can I start with the powder and make a dairy product that tastes exactly like the milk that's made, like the dairy product that's made with the milk? And the answer is not quite, okay? So we know from the recombining industry that if you take milk and put it into a powder, you can probably match some of these elements, but you're probably not going to match the flavor exactly, and you still probably have trouble with some of the texture. So that's taking the same material and just drying it and then rehydrating it, and it causes enough change that you have that level of problem. Okay. But then you've got the other approach, and I'll call this blindly I don't care because this is good and the rest of the other stuff that's bad I'm not even going to go to. And we won't get into politics. Okay. So here we have the Impossible Burger, which when we had one about 6 months ago at a restaurant in Nashville, Tennessee, was $3 more than the regular burger. Okay. They've got the looks down perfect, texture's not bad, taste is not bad. You throw it in a bun with a few other things, you have a beer on the side, you're probably going to be feeling pretty close, okay? But, and this is the upgraded, new, better label, okay? Soy protein concentrate, coconut oil, sunflower oil, potato protein, methyl cellulose, food starch modified. This is where they get a lot of their flavor from. They figured out that they could get a hemoglobin coming from a plant, soy protein isolate. These are just the makeup for the vitamins that you're losing by not eating meat. Okay. You know, this is just, if I'm on my little stand here for a moment, this is where you know, on one hand they'll say, oh, those are highly processed foods, those are god awful, you don't want to eat that. If this doesn't fit the definition of a highly processed food, I don't know what does, but it's got this health halo on it right now. So that's the challenge of scientists trying to make a rational conclusion about consumers. Okay. So I'll kind of end with this. And I still think that this is what we need to do, you know. And so I think if somebody asks me, you know, what kind of policies should we put forward for our food organizations or any organization that's funding research into food, especially looking at future food supplies, you know, I think you would have to address justification on all of these elements in the system, okay? That if you're doing something that's going to make a plant more sustainable with the change in a current, let's say in climate change, you also need to make sure that you're not changing anything that's affecting the processing down the line. You know, in fact, you know, this is why they did that with the tomatoes. They made the tomatoes hard so they can do mechanical harvesting. And we have an example of a food system, of an agriculture system where low cost has been the primary driving factor right now. We're going back on one where we're thinking more about the nutrients. So I think there's a lot of good challenges there, okay? And with that, I'll say thank you. I'll acknowledge, I did bold you, Marianne, so I don't know why you got unbolded, but you should be bold with the rest of them right there, okay? This is my last group that I had as a full group since I'm now fully retired as of June, and also you can never do any of this stuff alone. So Chris Dalbert was a longtime collaborator in the rheology, Marianne Drake in sensory, Dr. Marianne Lila here with bioactives coming in, my oral physiology person, my anatomy physiology person, and another good physical chemical scientist over in the Netherlands. So thank you for your attention. I'll be happy to answer any questions.